right, hello everybody. Am I coming in loud and clear? Can you smash that chat button if you can hear me out there? All right, thanks, Zach, ZG, Navnit, welcome to you, Daniel, Humphrey, Sishwan, Eric, Rossi, Siwen, hello, James, Han Young, hello, Floyd. Okay, glad you can hear me. I put up a little survey if you haven't already answered it. Which flavor of the writing assignment are you doing? So 25 have said pure maths, 2 electrical engineering, 9 economics, 2 civil engineering, and 7 taking chemistry. Like someone said in the comments, that's a lot of pure maths. Well, I hope it's going okay for you. As you know, last week, week 6 was flexibility week. So I did miss you because we had no classes, but I was getting very flexible. And I hope you had a good break or caught up on some things. In today's tutorial, we are going to look at complex numbers. Now, there are many questions from chapter 3. This is a tutor-led tutorial. So I'll be doing some of the questions, and you can come through and turn your mic on or do some chatting and just let me know how it's going. Okay, so yeah, let me share the questions and we can get started. So this is the main section, chapter 3. Now there are over 90 questions to do. So what I've tried to do in my Monday's tutorial is to do some questions there, and today I'll be doing some different questions, just to try to balance out all the ideas. Okay, so I wanted to start with question 10. Okay, and so this is an interesting question. But before we get to that, let's just remind ourselves what complex numbers are about. So firstly, some people, when they see the word complex numbers, they get really annoyed because it's like, oh, it's so complicated. But the idea behind complex numbers is to really make our lives simpler. So let me share my document camera with you and we can get started. All right, so I'm going to start with question 10. Just a few things before we start. So in complex numbers, you have this special imaginary unit called I, and it's defined to be the square root of -1, right? And so what this means is that the square of I is just equal to -1. So this is probably a super important thing. We don't write this very much, but we use this a lot. Okay, and in the complex plane, you can have, vertical axis and a horizontal axis. And this point here would be this general complex number. Okay, now you can also write a complex number in terms of lengths and angles. So you can also write it in this polar exponential form. Okay, so this is Cartesian and this is the polar exponential form. So pretty much all of those things are the basic building blocks of complex numbers. All right, so let me start with question 10. So in question 10, we're asked to do two things. And I can capture that just by using this. I'll do R instead of Z. Okay, so R is going to be the square root of this complex number where the real part of R is non-negative. Okay, so how do we solve that? That's the first part. And then there's a second part that asks you to calculate a different square root. Okay, so let's consider the following. So we'll consider this equation. And where R is just A plus IB. So we're going to solve this problem for R, and if we know A and B, then we know what R is. Okay, so let's consider this. So we're going to have A plus IB all squared equals 3 plus 4I. So let's expand this and we can form two equations. So if I expand this, remembering I squared equals -1, I'm going to get, who can tell me in the chat, what is the expansion of the left-hand side going to be? Who can smash that chat button? I'm a little confused now. What is the expansion of this going to be? Who can tell me? Who can tell me on the chat? If I expand this, what am I going to get? Come on, there's 69 people here. Yeah, Andy. Oh, yes, thank you. So if you look at Andy's chat and Zach's chat, they've both got negative b squareds in there. So it's going to be a squared. So let me write this out. So you guys are on the right track here. 2abi plus ib all squared. Now, we know that I squared is -1. So this is going to become negative b squared. Now, two complex numbers are equal if and only if the real parts are equal and the imaginary parts are equal. Okay? Yeah, thanks, Bowen. I can see your response too. So we get two equations here. We get a squared minus b squared equals 3. And 2 times a times b equals 4. So that's the same as ab equals 2, right? Now, remember we have this restriction here. So we know that a can't be negative. All right, so I'll show you a quick way of doing this problem. Okay, a very quick way. Now, usually for these questions, a and b are integers. They're whole numbers, right? So if you know that a is non-negative, what are the factors of 2? Can anybody tell me what a and b will be just by looking at this? What are the factors of +2? Who can tell me? Yeah, Nick, Jia Hong, Evan, it's not a trick question, absolutely. So the factors of this are 2 and 1. And you can see, well, if a is 2, then 4 minus 1 equals 3. So a's got to equal 2, which is greater than or equal to 0. B equals 1. That's it. Thank you, Evan. I can see your answer too. So when you do these problems, a lot of the time you don't need a third equation. You can just do it by saying, oh, what are the factors, and then making it work with this one. Pretty easy, right? Pretty easy. So we want to work smarter, not harder. So what is our solution? Hence, R is going to be 2 plus 1 times I, which we would just write as 2 plus I. Okay? So that's the first question. Now, for the second part, which I won't do all the calculations, you can similarly, believe it or not, that's similarly. If W is this, so now you've got 3 minus 4i, and the real part of W is, I think it's less than or equal to 0. Is that right? Let me just go back. Non-negative, so it's non-negative, so it's greater than or equal to 0. Yep. Yeah, Nick, there is a negative case, but you're told from the question that you don't want to worry about the negative case. Okay? So if you look back at the question, there's a good question from Nick. So let me just share the PDF again because it's a bit hard to bring that up. Nick brings a really good question here. Okay? R is the square root of that with non-negative real part. Okay? So usually I agree with you. You would get 2 answers, but we can throw one of them away. Okay? So we'll do the same with S. So that's a very good question, Nick. Thanks for asking that. So let me go back to my document camera. So then you follow the same steps and you get W is equal. So you would expand it, compare, do all that sort of stuff. And you'll get 2 minus I. All right? So just run the same argument. So now we've got these two things, and we want to simplify this expression, R plus S all squared. Okay, that's the final part of this. So we've got, oh, did I say W? I meant S here, people. Sorry, S. That's what's in the question. So that's an S. All right, so we're going to have 2 plus I plus 2 minus I squared. So the i's are going to cancel. You're going to get 4 squared. 16. Okay. So it's up to you which way you do these problems. Yeah, it's up to you which way you do these problems. So you can use 3 equations here if you really want to, but for simple problems, it's not necessary. Okay, it's absolutely not necessary in my opinion. So yeah. So this is, I know this is an S, and that's an S, believe it or not. Okay, so these kind of questions are classic Math 1131 questions. You see them in lots of past papers, and so they're worth knowing, and they're pretty interesting questions. So if you have questions, comments, observations, feel free to put it in the chat. Let me know what you're thinking. Okay, let's keep on going. All right. Let me have a look at what's going on here. All right. Let's have a look at number 20. So let me share my PDF with you. Now remember, I have done some of these in my Monday tutorial. Okay, it's a H1, but I think it's really important to discuss, because you are going to see a lot of questions like this. All right, Lucas, let me have a look at question 8 in a minute. I'll see if I can come back to it. Okay, thanks for asking. So here's a complex number. Calculate the powers of the complex number and plot them on an Argand diagram or in the complex plane. Is there a pattern? Okay, so this is a really cool question. So let me discuss it with you. Okay. All right. Sorry, there's a lot of notifications coming through on my Microsoft Teams. So let's have a look. I'll share my screen with you on my document camera. Okay, so this is 20. So consider this complex number here, 1 plus I. Okay, so what we want to do is compute the powers of that complex number. Now, there's a fast way to do this and a slow way to do this, and I would prefer to do it the fast way. Okay, so let's transform this Cartesian form into polar exponential form. Yeah, Euler form. Digi, you're right. So if I just do a basic plot in the complex plane, this is the real axis, this is the imaginary axis. What I need is the length from there to there and this angle. Who can tell me the length and the angle? Who can tell me in the chat? The length is, yeah, √2, absolutely, and pi on 4 radians or 45 degrees, okay? So we don't really even need to do any calculations. We can just draw a picture and work it out. Okay, so the √2 is from Pythagoras and the pi on 4 is just basic trig, right? So if you want to do, I mean, you can do a little right-angled triangle here and, you know, set it up that way, but I like to avoid it if possible. Okay, so now consider, please, z to the power j, let's say. Okay, so that's going to be √2 e to the pi I on 4 all to the power j. And j is just an integer that goes up to 10. Okay, so it's pretty easy to calculate this when you have this form. Okay, like when you have the polar exponential form, it's much easier. If you were to expand this, it would not be fun. Okay, but this is super fun. Okay, it's super easy. Okay, so what's going to happen? Well, from the picture, when you multiply a complex number, you're basically adding the angle and you're multiplying the length. So we kind of know that the next one should end up on the imaginary axis because there's 45 degrees. There's 45 degrees there and there's 45 degrees there. So you add the two angles and it's going to take you there. Next one should be there. The next one should be real. The next one should be there. The next one should be there. Blah, 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 blah. Okay? Hopefully you get it. So let's try it. So z squared is going to be this. So you'll just expand it like you normally would. So that's going to become 2 pi I on 4, which is pi I on 2, and I end up on there. Okay, that's actually just going to be 2i. So I go out there. Okay. So now what? Well, let's try again. Z cubed. Well, let's go back here and see if we can work it all out. Okay, well, that's going to be 2 root 2 times e to the 3 pi I on 4. Okay, so now we're sort of out here. That's where we are. Okay, so what's the next one going to be? Well, the next one's going to be another pi on 4. So you're going to get back to the real axis. Let's see if it really works. Okay. So that's going to be this to the power 4. So that's going to now become, that's going to become a 4. And that's going to become e to the pi I. That's going to be all the way over here, -4. Okay, so can you see the pattern? The angle is always the same, but the length is increasing by a factor of square root 2. Okay, so you can continue this, all right? So if I won't do them all, but each calculation turns an angle of pi on 4 in the anti-clockwise direction or counterclockwise. And the magnitude or the modulus, the length, is scaled by a factor of root 2. Okay? Oh, Zach, I think it'd be pretty unlikely that you would solve all the way. You wouldn't get a question like this. I would be very, you know, because why would they ask you to do 10 things that are the same? Does that make sense, Zach? I wouldn't, you know, why get you to do 10 things when it's just the same as doing 4 things? But there are a couple of other questions here. So let's go back to the PDF because there are some interesting questions here, no doubt. Okay, so is there a pattern? You bet there is. Yes, there is a pattern. Okay, when you multiply 2 complex numbers, you add the angles. Same thing going on here, and you multiply the lengths. Okay, what is the smallest positive integer such that z to the n is a real number? Who can tell me in the chat? We've worked it out just from the picture or from our working. What is the smallest positive integer n? Just from what I've shown you, such that the power of z is a real number. Yeah, Andy, Hattie, awesome. Okay, Nick, yes. So if we go back to our document camera, you can see that's purely imaginary. That is sort of out there. And then this one, out there, that's real. Okay, so it's n equals 4. It is n equals 4. So note for n equals 4, our z to the n is a real number. Yeah, that's it. So the most important thing with this type of question is that you can see that you're going to get, you know, you're going to break it up into bits when you take the powers, okay? And these angles are always the same. Yep. And then you're going to get some repetition too, right? You're going to get some repetition. So, you know, you'll start, if you continue this pattern, you'll get back to the same places that you were before, which is pretty interesting. Okay. Yeah, I've got Iron Man in the background today. Hello. All right. Okay. So, Zach, what makes it real? It's, okay, so let me show you my picture again. It's a good question. What makes it real? This is the real axis. It's like the number line. So anything that lies on there must have just a real component and zero imaginary part. Okay? Does that make sense? Yeah. So, okay. Yeah, that's it. People are jumping in on the chat. Keep it going, people. That's right, Evan. Good job, and everyone else. Okay, so question 8. Who was asking about question 8? Was it you, Lucas? Yeah. So I can show you a question. I'll do the first one. There is a video solution for this, but let me just show you the first one, and then you can do the other parts if you want. So question 8, and I'll show you the question. Here it comes. So you see the V, it means that there are video solutions, but use the quadratic formula to solve these, these polynomial equations. Okay, so it's just a standard way of applying this quadratic formula to new problems. So let's have a look at one of the questions. All right, so this is part A, and I'll leave the rest for you to do, because once you've seen one of them, they're pretty much all the same, except for part E. So if you know how to do part E here, put it in put your strategy in the chat, okay? So we want to solve z squared plus z plus 1 equals 0. Okay, so you can think of this as a quadratic equation, and the coefficients are your A, B, and C. Okay. All right. And based on A, B, and C, we can apply the quadratic formula. So A would equal 1, B would equal 1, oh, and C would equal 1. Isn't that nice? Okay, so what is the quadratic formula? Well, quadratic formula is the solutions can be written like this, okay? And so the plus or minus gives you the two solutions. As people were saying before, this is a quadratic with real coefficients, so you would expect two solutions, and there'll be a special relationship between the solutions that we'll talk about in a minute. Okay, so let's work this out. So negative b will be that, b squared will be 1, 4ac will be negative 4, like that. Okay, all over 2. So what we end up with is this. Okay, whoops, yep. So how do we manage this away? Well, I can write this in the following way. Okay, you have to be careful with these kinds of calculations, but you can write negative 3 as 3 times negative 1, And that can be written as 3 times I squared. Okay, but be really careful when you're doing this sort of stuff because, you know, you might have seen those YouTube videos where people do this sort of stuff and they say, aha, I have proved that positive 2 equals 0 or something like that. Okay, so we'll get that. And there you have it. Okay, so that's one way of doing it. Another way is called completing the square, but you know, I'll just do it that way because that's what I think they want you to do. Okay, Lucas, is that ringing any bells here? Does this quadratic formula look familiar to you? Yeah, so the only difficult thing is managing this away. Okay, that's the only difficult thing. And so you can just do that using a little bit of algebra very carefully. Well, Zach, if you want to, you can go like this. It's like -1/2 plus I root 3. That's one solution, and -1/2 over 2, and -1/2 minus I root 3. Okay, they are your two solutions. Okay, now what is the relationship? Who can tell me in the chat what is the amazing relationship between these two solutions? How are these two things connected? Who can tell me? What is a relationship? Oh, reciprocal. That's a good try. What do you mean by reciprocal? Yeah, Chloe's jumped in and Han Yang, thank you. Yep. So if I was to plot these things in the, say, in the complex plane, -1/2 plus that, which might be there, and the conjugate is there. Because you know that the conjugate is a reflection in the imaginary axis. Yeah, boy, Nick, you're on it, man. So why does this matter? Why does this matter? Because once you have one solution, you get the other one for free. Let me give the big close-up. If you know that the solutions are conjugate pairs, you only need to calculate one solution because you get the other one for free. Kaboom! It's amazing, right? That is amazing. You want to work smarter, not harder. So let me give you another example. If you're solving some z to the power 6 problem, right? And you know that the solutions occur in conjugate pairs. All you got to do is calculate 3 solutions because each of them have the conjugate pair as a solution. Wow. Okay, so it's an amazing thing. Okay, so let me go back to my PDF. And yeah, okay. So I've done that one. I wanted to do, where are we? What number is that? Yeah, okay. So I wanted to have a look at 25. Now, 25 has a H, but it's actually not that hard. It's pretty easy. And the idea here is to get you using the basic properties of the conjugate. I think that's why it's there. Okay. So let's have a look at 25. All right, so just need to find my Sharpie. Yep. No. I've gotten so excited that I've just lost my pen. Oh, there it is. Okay, Iron Man must have taken it. Okay, so they give you a hint. Let's use that to prove that. All right, so this is 25. All right, back to the document camera. So I think with this one, it's just the old left-hand side equals right-hand side type of argument. Okay, so you want to prove the following. 1 minus z bar w squared minus this. So we're talking about the modulus here. All right, and they give you a little hint to use the properties of the conjugate. Straighten that up. So you can do this a few different ways. I'm just going to start with the left-hand side and expand that and use the basic properties of the product of a conjugate with the complex number. Okay, so left-hand side of star equals this. So let's use this basic. Let's use this thing here. Okay, so that's true for every complex number v, and we'll let v be this mess inside it. Okay, here, and we'll do the same thing over here. Okay, so I'm going to get 1 minus z bar times w times 1 minus z bar times w, and that's all conjugated. Minus, we'll do the similar thing with this. Okay, and so this is a bit weird, but you can break these things up. So with the conjugate, if you have a sum or a difference, you can break it up into the sum or the differences of the conjugates. So let's do that. So it's the conjugate of 1 minus the conjugate of that. So who can tell me in the chat, what is the conjugate of 1? What is the conjugate of 1? Who can tell me? It's not a trick question. Correct, James. Excellent work. So I end up with that. Okay, so I've broken that up. The conjugate of 1 is just itself. Okay, and let's do that here. Okay, so now what do we have? We have the conjugate of a product. Now the conjugate of a product is the product of the conjugates. So this is pretty easy to do too. Now this is not an equal sign. That's the conjugate of the conjugate. Oh my goodness. We're getting a bit out of control now. Okay. All right. So what is, who can say in the chat, what is Z bar bar? Z bar bar. I don't mean Z88. I don't mean Z88. Yes, it is Z, right? So the conjugate of the conjugate is just the original thing. Okay. So, yeah. So 1 minus Z bar W is 1 minus Z times W bar. It so sounds like the number 8 in Chinese. Okay. So now we can expand these things out. Okay, so you're going to get 1 minus ZW bar minus Z bar W plus, now Z bar times Z will give you that squared. W times W bar will give you that. Okay, and so down the bottom, We're going to have something like this. Z times Z bar, that's Z squared. Z minus W bar minus WZ bar plus this. Okay? So you're going to get the cancellation now. So that's going to cancel with that. That's going to cancel with that. And what you're left with can be factorized into the right-hand side. And this is the right-hand side. Okay? So there it is. Okay, not a difficult question, but lots of conjugates and conjugate properties. I think that's the aim of this question, is to get you thinking about all the nice properties of the conjugate. Okay, let me just turn that lighting up a bit. Yeah, maybe that's better. Yeah. Okay. So the final part of the question, let me just share my PDF. I'll come back to this in a second. So we want to deduce that this is true if either Z or W lies on the unit circle. So who can tell me in the chat, what do we mean mathematically when we say Z or W lies on the unit circle? What do we know about the magnitude or the modulus of Z and W? Who can tell me in the chat, what do we know about the modulus or the magnitude of Z and W if they lie on the unit circle? Yeah? Yeah. So you're all on the right track. It'd be something like this, right? Yeah. And yeah. So let's go back to our picture with Z bar, Z, a modulus of Z equals 1 and modulus of W equals 1. So if that's 1, then this is 0. So this left-hand side becomes 0 and you get the thing you're looking for. If this is 1, then this bit disappears, so this disappears, and it's also true. Okay, so I might just put a little if this is true, then this thing will equal this thing because this is 0 over here. Okay, so that's the very last part of the question. The very last part of the question. Okay. There is one final question I wanted to do. And this is a question, let me just see if I can find it. Yeah, it's 29. Okay, so let me see if I can find my solution here. And then we can finish up. Yeah. Okay, so let me put this up. So 29, it looks like a difficult problem, but actually it's very easy if you know what to do. Okay, so we want to solve the following. We want to solve this, and we're told that the answer, theta, is between negative pi and pi. Okay, So how do we do it? Well, there's an algebraic way of doing this problem, not like that, but I want us to work smarter, not harder. So remember that we have a special formula called Euler's formula. It gives you a relationship between this and this. And what does this thing look like in the complex plane? Well, imagine a complex number that this is like the x component and this is like the y component, okay? What it says is that all the points on this just lie on a circle in the complex plane. Okay? So what this is trying to ask us to do is say the distance between the circle and the point 1, think about this, is equal to 2. So what points on the circle are 2 units away from this green point? Who can tell me in the chat? Let me say that again. What points on the circle are exactly 2 units away from this green point? It's not a trick question. Evan. -1. That distance is 2 units. Good on you, Evan. Okay? That's saying the distance between the points on the circle and +1 is exactly equal to 2. So what it's saying is this is the point. Now, who can tell me what is the value for the angle theta at that point? Who can tell me in the chat? Yeah, pi. Does that fit with this? Yes, it does. So this is how I would do it. From the diagram, we see that this, and that is 2 units. Bump, bump, bump. Okay. Now there is, of course, another way to do this problem. This is the first solution. Okay. If you don't like drawing pictures, then you can solve this problem, right? You probably want to use this and go, oh, well, it's cos theta plus I sine theta minus 1. You know, you probably want to square both sides, and then you can, do that and expand it. And then you want to use cos squared plus sine squared equals 1, blah, 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 blah. And you get down to something like this. Yeah? And so you're basically solving cosine theta equals -1. So you can sort of do that. Okay, so you know it's got to be there. Which one do you prefer? Do you prefer this way of doing it? Do you prefer 1 or 2? Which solution method do you prefer? Let me know in the chat. Let me know. 1 or 2? No. Which one is working for you? Solution 1 or solution 2? Mm. 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 Yeah, they both have advantages and disadvantages. Yeah, this is a good method, but it's very algebraic. But this is how most students would solve the problem. This I really like this because it's very easy to work out what's going on. Yeah. So Nick makes a good point here. This method is probably less flexible than this method. So I think Nick's saying, well, this is a good method because it's very versatile. Is that right, Nick? Yeah. Yeah, I agree. I agree. All right. Let me come out of hiding. So look, it's been great seeing you again, everyone. Last week in week 6, I had no classes, and I was like, oh, what do I do again? I was a little like bored and confused. But yeah, just enjoyed another class with you and enjoy the week.